In this video, we'll talk about undamped forced oscillators and how the situation is different from that for a damped forced oscillator. So if there's no damping, then the problem changes a fair amount. Right now we just have an equation of the form a y double prime plus cy equals f0 cosine of omega t, and there's no damping coefficient anymore. What do our solutions look like for the homogeneous problem here? We can just solve it however we want. We have a r squared plus c equals 0. So r is plus or minus square root of negative c over a, which is root c over a times I, which means that our general solution here is, for the homogeneous problem, is c1 times cosine of root c over a t plus c2 sine of root c over a t, or in the more common notation, setting omega 0 to be this root c over a, which is the natural frequency of the system, we get a c1 cosine of omega 0 t plus a c2 sine of omega 0 t. Notice here, since there is no damping, this does not decay to 0 as t gets large. We can also work out the non-homogeneous part of the equation. And for that, by undetermined coefficients, we're just going to plug in a cosine of omega t. We don't need the sign here because we only have two derivatives and no derivatives, which are both going to stick on cosine. So the sign term's just going to vanish at the end. So we're just going to plug in this. And we'll basically see that for that, we want to have that negative a times little a times omega squared cosine of omega t plus little c times big A cosine of omega t equals f0 cosine of omega t, which means I need that f0 equals c capital A minus a little a omega squared, or that's solving out for big A should be f0 divided by c minus a omega squared. Or if you want to write in a slightly different form, f0 over a times omega 0 squared minus omega squared, because c over a will be omega 0 squared. So in that case, we get a full general solution that is a c1 cosine of omega 0 t plus a c2 sine of omega 0 t plus this constant times cosine of omega t, and this is all under the assumption that omega 0 is not equal to omega. We'll deal with that case separately later. But the point to realize here, nothing decays away. So there's going to be some sort of long-term interaction here, and the initial conditions continue to matter throughout the entire problem, instead of just decaying what they do in the damped case. The situation here is a fair amount different than that for damped forced oscillations, and there's a couple examples to what behavior can occur with these equations that cannot occur in other situations. And it mainly comes from how these different cosine and sine functions interact with each other, because you basically have two different waves of different frequencies here. You have omega 0 t, it's going at a certain rate, and omega t at a different rate with this sort of constant going on here. And they're going to interact somehow, and the ways in which they interact can affect a lot of what the outcome looks like, what can happen with the system, and whether or not this model breaks down based on what happens when these waves interact with each other.